Hi, my name is Kruliš and it is my pleasure to present to you our artifact called Simdex. Simdex is basically a simulator accompanied with a dataset which is based on a backend of a real existing system. This simulator is designed to test various self-adaptive strategies and evaluate them using custom metrics. Before we get to the description of the artifact, I would like to say a few words about our motivation. In our current line of research, we are focusing on machine learning and its applications in self-adaptive systems. Although the machine learning is a very hot topic which has improved various domains, its applications in self-adaptive systems are still sparse. To experiment with machine learning, we typically need to design simulations of self-adaptive systems. Creating the simulations is necessary since real systems are too complex, and we often do not have enough real data to train machine learning models, so we need to gather these data from simulations. Unfortunately, this approach often amplifies possible threats to validity of such research. The main problem is that the author of the simulation is also the author of the machine learning model that is designed to rediscover the principles implemented in the simulation. Therefore, we have decided to create a simulator based on a real system that uses real data. The system we have selected as a basis for our simulator is called Recodex Code Examiner. It is an education tool for evaluation of programming assignments. Its key principles are based on well-known software engineering methods for automated code testing. To give you a better idea, let me briefly describe the fundamentals. The teachers give students coding assignments and the students submit their solutions in the form of a source code. The source code is compiled and executed in special sandbox, which is also designed to measure performance characteristics like execution time or consumed memory. The outputs are validated by a judge that determines whether the solution is working correctly. This process can be repeated multiple times for different inputs to cover corner cases or to estimate asymptotic complexities of the solution. The judge results and measured characteristics are used to assign score to the solution, and the results are presented back to the student as a feedback and to the teachers so they can be used for grading. This system has been successfully deployed in our institutions for about 5 years, and it assists teachers from over 20 courses. We have focused mainly on the Recodex backend, which offers some opportunities for improvement by using self-adaptive methods. The backend is responsible for compilation and evaluation of the solutions, which is performed by independent worker servers. The main reasons are that the evaluation may take quite a long time and we don't want to saturate the front-end server. Furthermore, some assignments require precise time measurements, so the worker needs to be dedicated only for the evaluation. In our simulation, each submission is represented by an evaluation job. The jobs are assigned to the worker queues and processed non-preemptively in the first-comes, first-served manner. Each job is assigned to a queue immediately after it is spawned, and it cannot be reassigned. The key problem here is that it is difficult to predict how long a job will be evaluated by a worker. Even submissions from the same assignment may end very quickly, if the compilation fails, for instance, or take quite a long time to process if they contain an infinite loop. So our Simdex artifact is composed of two parts. The first part is a dataset which was assembled from Recodex submission logs and solution metadata. That comprised mainly the time when the job was submitted and how long did it take to evaluate on our hardware. Each job have also additional metadata which can be used for various purposes, most importantly for training machine learning models that would predict the evaluation time. The simulator basically reads and replaces the job logs and simulate the worker queues. It is designed so that the user can inject custom code that governs job dispatching and its self-adaptation. Furthermore, the simulator can be configured to collect predefined as well as custom metrics that can be used to evaluate the job dispatching strategy. The simulator architecture is presented in this schema. Log reader is responsible for loading the job records and passing them to the dispatcher, who immediately puts them in worker queues. The dispatcher employs custom algorithm, which itself is static, but it can be affected by the dispatcher configuration and by the worker queue properties. Second custom module provided by the user is the self-adaptive controller, which implements the self-adaptive strategy. We rely on the traditional Maypack loop, however, its implementation is solely in the hands of the user. The self-adaptive strategy is invoked periodically, as well as just before each job is given to the dispatcher. The strategy has full access to the status of the whole system, and it can choose to modify the configuration of the dispatcher or to adjust the parameters in the queues. As mentioned before, the dataset comprises the submission logs from real students. To be precise, it holds logs collected since October 2017, when the current generation of the system was deployed. The dataset was duly anonymized to ensure sufficient data privacy for our students and filtered so it does not contain potentially problematic records of jobs that failed due to internal errors or infrastructure failures. We also provide an additional dataset of reference solution jobs. Reference solutions are submitted by teachers to verify the assignments before they are given to students. These solutions may be used as basis for creating better estimators for how long regular jobs could take to evaluate. Just to give you a basic idea, the dataset comprised nearly 400,000 records, and up to date it covers 27 separate courses. These are the most important properties associated with every job. The most important ones are the timestamp and when the job was created and how long the evaluation actually take. The group IDs, the exercise ID and the runtime ID, the programming language, can be used to better identify the type of the assignment being solved. It is also important to realize that even that all properties are available in the dataset, the dispatcher must refrain from reading the duration and the correctness, since these values are the logical outcomes of the evaluation. To evaluate our simulator and to provide a demonstration of utilization, we created two sample scenarios with different optimization objectives. The first scenario entertains a simple yet important idea. The objective is to reduce consumption of resources, namely the electrical power, when the system is underutilized. For that purpose, we assume that there is an efficient mechanism that will allow the system to turn the servers off and wake them up again. This mechanism is represented in the simulation by the active flag associated with each worker queue. To ensure at least some basic latency, we added a rule that at least one worker must be running at any given time. In this scenario, the dispatcher algorithm is very simple. It checks the status of all queues and selects an active queue which has the least enqueued jobs inside for dispatching. The self-adaptive strategy can adapt the system by turning workers off and on. We have selected two metrics for the evaluation. The first one monitors the delay of each job. That means how long each job spent in the queue before its evaluation started. The second one measures consumed electrical power based on how long each worker was running. There are many possible strategies how to handle the activation or deactivation of the workers. We have implemented a simple self-adaptive strategy based on two rules. The first rule is designed to wake sleeping workers if at least one worker queue has more than one job. In other words, when at least one job must wait for evaluation. The second one turns workers off when there is more than one idle worker in the system. This rule also implicitly ensures that there will be always at least one running worker. We have compared this strategy with two baselines. The baseline algorithms use the same dispatcher but no self-adaptive module, so their number of workers was constant during the entire evaluation. As expected, the one-worker baseline exhibits the lowest power consumption because only one server was running. On the other hand, the job waiting times were significantly higher. The four-worker baseline achieved much better latency at the cost of 4 times higher power consumption. As you can see, the self-adaptive strategy is quite close to the best values from both baselines. It shows only small decrease in job delays, but it also has only 5% increase in the power consumption with respect to the optimums. The second scenario is slightly more elaborate, as its objective is to improve user experience. It is based on the assumption that the users will actively wait for the results in case of short-running jobs and prefer to be notified when the results become available for the long-running jobs. That also means that the short-running jobs should be prioritized in the dispatching to make sure the users will get their results soon, while the long-running jobs can be delayed significantly longer without the users noticing. Unfortunately, the job duration is not known at the time of dispatching. Actually, the duration is present in the data, but the dispatcher should not read it. Therefore, the dispatcher must rely on the job duration estimation, which may be an interesting machine learning problem. The dispatcher itself works as follows. Each queue has specified a time limit in its attributes. The dispatcher can place a job in such queue only if the duration estimate is lower than the limit. This way, we can create dedicated queues for short jobs. The evaluation is slightly more complicated. The average job delay is still being used, but only as a secondary metric. The primary metric is based on 3-bin histogram that is computed from the job delays. Each job is classified as either on time, delayed, or late, based on its ratio between the actual delay and the computed duration estimate. Comparing these histograms may give us a slightly better idea than simply comparing the delay averages. Again, there are many possible ways how to design self-adaptive strategy. Actually, in this scenario, we can adjust multiple things, including the time limits. However, the main purpose of this example was to demonstrate that Simdex is ready for direct utilization of machine learning models. Thus, the only thing being adapted in our case is the prediction model for the job duration estimation. The model is stored in the configuration of the dispatcher and it is updated by the self-adaptive controller. The controller collects metadata from the jobs and retrains the model periodically. We have implemented two models. The first one is very simple and only computes statistics for job durations categorized by exercise and programming language. In other words, the estimate duration is the average duration of all previous jobs in the same category. The second model uses artificial neural networks that perform regression utilizing all job properties as inputs. The neural network was implemented using TensorFlow, which is a well-established machine learning framework. Since our simulator is written in Python, TensorFlow can be used natively in the same code. We have compared the two machine learning models with two baselines. The first baseline is static and uses only the exercise time limit, which is basically the theoretical maximum for estimating the job duration. The second baseline represents the hypothetical optimum. It violates the causality of the simulation by accessing the actual job duration and using it as the estimate. Although such strategy is not applicable for the real system, it gives us an idea how would the simulation perform if we had the ultimate estimator. As expected, the performance of machine learning models is in between the baselines, but we can safely say they are much closer to the theoretical optimum represented by the Oracle baseline than to the static baseline. Furthermore, both models exhibit very similar results. The statistical model is slightly better in the primary metric, but the neural networks show better average delay. In conclusion, I would like to summarize our contributions. We have presented Simdex artifact, which comprise a simulator of a backend of a real system and a dataset that represents workload logs that can be replayed by the simulator to test different self-adaptive strategies with different optimization objectives. Our simulator is highly flexible and customizable and directly ready to be used with state-of-the-art machine learning frameworks. The dataset itself can also be used for other experiments where realistic workloads need to be simulated. The whole artifact, including the documentation, is available at GitHub, along with the original Recodex system. You are welcome to explore them at your leisure. Thank you for watching, and I am looking forward to your questions during the online session.